Hi guys, we're back with another video on Laplace transforms, this time section 10.5. We're going to be talking about the first shifting theorem today. Okay, as normal, prerequisite skills, and this is actually the first shifting theorem. We're just going to come up with some adaptations for our standard Laplace formulas. So for this, we just need our Laplace transform formulas. And maybe some rudimentary algebra. A couple algebra skills like completing the squares, things like that. Okay. So let me explain to you what the first shifting theorem actually says. And what it does is it actually draws a parallel between two quantities. So first of all, suppose I have the Laplace transform of e to the at times f of t. So this is, it's a new function, right? So it's a product of this exponential function and f. And if I take this as an entire function, then by definition, the Laplace transform should be the integral from 0 to infinity of e to the negative st times my function, e to the at f of t dt. But I can rearrange this just a little bit by combining these two terms, multiplying my like bases here. That's going to give me e to the negative s minus a t times f of t dt. Okay, sure. But this is f of s. By definition, f of s was this Laplace transform of f is the integral from 0 to infinity of e to the negative s t times f of t dt. And what we notice is that the distinction between this formula and this one is that I've just made a substitution. The only distinction between here and here is that I've substituted s minus a for s. And so drawing that same conclusion here, I have f of s minus a should be the integral from 0 to infinity of e to the negative s minus a t f of t dt. And so that's the same, right? That's the exact same. And so from this, what we get is, we get that, so drawing that this is equivalent to this, and hence equivalent here, what we get is that if you would like to take the Laplace transform of an exponential function multiplied times another function, what you get is just the Laplace transform of f, okay, shifted to the right a units, right? That's why it's called the first shifting theorem. We've shifted this to the right, okay? So in order to use this, what we would like to do is we would like to find the Laplace transform of the secondary function and then shift that to the right a units. Okay, so let me do an example and then we'll come up with another list of formulas to replace the ones we learned in section 10.1. Okay, so for example, let's let h of t be e to the 2t times cosine t, right? All right, so what I'm going to do here is I'm going to look at the second function here, cosine of t, okay? And I know that the Laplace transform of cosine of t is s over s squared plus b squared, but in this case b is 1, so 1. And so what I'm going to do is I'm going to take this and shift it to the right 2 units. Right, so I'll shift that to the right 2 units. Let's see what that gives me. So that gives me that the Laplace transform of h of t is, so it's this one, shifted to the right 2 units, that's s minus 2 over s minus 2 squared plus 1. Yeah? That's it. That's That's how the first shifting theorem works. And so, and again, in reality, did I need to fill in numbers here for A and B? No, I can. Those were somewhat irrelevant. I'm about to write out the formulas without actually using those. But this gives me a way to find Laplace transforms of some products of functions that we've already been using, specifically the product of an exponential function and one of these other ones. So let's go ahead and get a list of my adapted formulas here. I'm going to put these in a different color. We'll use blue. Why not? I like blue. Okay. So let's see. We had, obviously I don't need to use the product of an exponential function and an exponential function, right? But let's see. So let's say, no, we did this one already. So we'll have the Laplace transform of e to the at cosine bt. That's just s minus a over s minus a squared plus b squared. Okay. We have the Laplace transform of e to the at sine bt. Okay. Now remember, sine was b over s squared plus b squared. So again, just replacing all of the s's with s minus a, we get b over s minus a squared plus b squared. And then lastly, of course, we'll have our polynomial term, t to the n power. This was n factorial over s to the n plus 1. So, okay, let's undo. We'll have n factorial, and instead of s, we of course just have s minus a to the n plus 1. Okay. So these are our basic Laplace transform formulas adapted to the first shifting theorem. Obviously, you can apply these in the exact opposite direction to get some formulas for the inverses. Okay, so things like the inverse Laplace transform of s minus a over s minus a squared plus b squared is just e to the at cosine bt. It's the exact reverse direction of these. I'm not going to write the other two out, but again, you can extrapolate those from these formulas. Okay. Okay. In practice, going forward, taking these is just a matter of following the formulas, right? So there's nothing tricky about that. Going backwards, on the other hand, we can run into some interesting algebraic issues. So I want to do maybe a couple examples where I have to go backwards. Not too many, but just a couple examples where we have to go backwards. The first is that we may get some more interesting partial fraction decompositions. So for example, let's do the inverse Laplace transform of, let's say, s plus 1 over s minus 2 cubed. Don't know, I'm making that up off the top of my head. It might turn out badly. So again, I know I need to decompose this. So I know how to decompose this fraction. I guess I'll use red. So I know that s plus 1 over s minus 2 cubed is a over s minus 2 plus b over s minus 2 squared plus c over s minus 2 cubed. Again, multiply through gives me through by s minus 2 cubed gives me s plus 1 is equal to, we got what? A times s minus 2 squared plus b times s minus 2 plus c. So again, this is true for all possible values of s. I can get a nice cheap value here by plugging in s is equal to 2. Gives me 3 on the left. These two terms are dead, so I get c is equal to 3 over here. At that point in time, I need to start looking for some other types of terms. Why don't we go ahead and look at the c is exclusively a constant. So we can look at the the quadratic terms, there's only one, so that should be pretty easy. So s squared. On the left-hand side, I've got 0s squared. And on the right-hand side, if I were to expand s minus 2 squared, I would get s squared minus 4s plus 4. But more importantly, I would get a times s squared. No other terms contribute to any s squared terms, so I get 0 is equal to a. Now that I know that a is 0 and c is 3, I can look at maybe the constant term from these equations to give me a little bit more information. Constant term on the left is 1. On the right, it's going to be 4 times a, b times negative 2, so minus 2b, plus c. Now we know a is 0, so 4 times a is nothing, and c is 3. So 1 is equal to negative 2b plus, not c, 3. We make that substitution. Okay, 3. This gives me b is equal to 1. Right? Subtract 3 over, divide both sides by negative 2, I get b is equal to 1. So I know that I can rewrite this. This is equivalent to the inverse Laplace transform of, let's see, a is 0, so b is 1. So I get 1 over s minus 2 squared plus 3 over s minus 3. S minus 2 cubed. Okay, and now we're ready to invert. Okay, we couldn't have inverted directly from the original, obviously, because again, this is clearly an exponential and a polynomial term. Again, it's s to a power that's been shifted to the right too, and those have to have constants in their numerators, right? They're not allowed to have s's in the numerator. So let's go ahead and see if we can't untranslate these, right? So this is a shifting for 1 over s squared. And this is a shift of 3 over s cubed, right? So I know that the inverse Laplace transform for this one, okay, is, all right, this is 1 over s to the n power. This is t to the n minus 1. So 2 minus 1 is 1, divided by n minus 1 factorial. So, and then this one, if I untranslate this, this would be, again, 3t to the n minus 1. So 3 minus 1, that's squared, divided by n minus 1 factorial. That's 2 factorial. And so I see here that, again, just translating 1 over s squared, this is just t. And translating 1 over 3 over s cubed, I get 3 halves t squared. And of course, because of my formula here, I know that it's just the product of e to the 2t times each of these functions. So I've got e to the 2t from the shift, t from the untranslation. Here I've got e to the 2t from the shift. And then from my untranslation, I've got 3 halves t squared. Okay? And you can write that in whatever order you want, factor out an e to the 2t and a t, whatever you want to do. It's fine. Okay? Yeah? So again, not overly complicated, right? Maybe we've got to do some partial fraction decomposition. Maybe we have to do some other clever things. I want to do one more example for you, just to show you some of the other things that may come up. Might be just a little unpleasant. Okay, but I guess not even unpleasant. Let's be honest. They're fun, right? But it requires a little bit more effort than sort of the standard inverse here. Okay, so I got an example marked here. Here we go. So I would like to untranslate. Here we go. So f of s is equal to 1/2 s plus 2 over s squared plus 6s plus 13. So s squared plus 6s plus 13. Okay. Okay, so first things first. you're going to want this numerator to be monic, right? I want the coefficient for s to be 1. The reason is when I see an irreducible quadratic, this is not factor, right? This is an irreducible quadratic. When I see an irreducible quadratic, I know this is going to turn out to be a sine and a cosine, right? Right? Now, the key here is I want to make the cosine first. The cosine is going to involve a more particular numerator, right? For sine, it's just going to be b over s minus a squared over plus b squared. But for cosine, it's got to be s minus a. Specifically s, 1s, right? So monic. So the first thing I'm going to do for all of these things is I'm actually going to factor out whatever this coefficient is for my s here, right? I'm going to factor that out because it's going to make it a lot nicer for me. So, all right, and this might happen. So the first thing I'll do is I'll make it monic. Let me just take the 1/2 out. That's going to give me s plus 4 over s squared plus 6s plus 13. Okay, that's first. Okay. The next thing I'm going to do, because I'm going to need to know how to break these things apart, is that I'm going to notice that this denominator is not in the form I'm looking for. What I actually want is I want something that looks like s minus a squared plus b squared. And you might notice this is the form you'll get if you complete the square in your denominator. So again, that's what I want to do next. I want to use completing the square to rewrite my denominator in this sort of completed form. All right, so let's do that. Okay. Still got my 1/2 here. Numerator's not going to change. I'm going to need to do some things to the numerator, but I'm going to want to fiddle with my denominator first so I know what I need. Okay. So let's see. I've got s squared. I've got 6s. And I've got a 13. I'm leaving some space here to complete the... Now, I know all of you know how to complete the square, but I'm going to go over it just maybe real quickly one more time. I'm going to take half of my linear coefficient here. That's this one. So half of my linear coefficient, half of that 6. I'm going to square it, and I want to add that, right? So half of 6 is 3. Square that, you get 9. I want to add 9. Now, the problem with adding 9 is, of course, I'm not allowed to add 9. Yeah? That's... I mean, we're only allowed to multiply by 1 and add 0, so unfortunately, or fortunately in this case, I need to subtract 9 to balance that back out, right? So I'll add 9 and I'll subtract 9. Now, that's really not that bad, okay? Because what I'm going to do is, I'm going to take those 3 terms at the front, so s squared plus 6s plus 9. And those I know are going to factor. They're going to factor into a very nice square. S plus 4. All right, so let's see. S squared plus 6s plus 9. That's s plus 3 squared. And then the remaining 2 numbers are just arithmetic. Minus 9 plus 13 gives me positive 4. Okay, so from here, I can already tell you what I need A and B to be in order to fit my formula for either s minus a over s minus a squared plus b squared, or b over those things. If I'm looking at this, I can already tell you from right here and from right here that a is going to be negative 3 and b is going to be 2. That's b squared, remember? Okay, so first things first. I'm going to make the cosine first. And to make this into cosine, what I really want is, I really want s plus 3 over s plus 3 squared plus b squared. Because again, that's the formula for the inverse Laplace transform for this first shifting theorem. It's s minus a over s minus a squared plus b squared. So what I'm going to do is I'm just going to split this fraction. Okay? I'm going to split this fraction. I'm going to take off what I need. Now, there's a couple ways to do this. You can clearly see I've got s plus 4, and so what I could do, I could just write this as s plus 3 plus 1. That will give me the s plus 3 I can pull off. Okay? I'm going to show you to do this a little bit differently in case this number doesn't come out nicely. So this number was like 2/13. Right? If this constant was 2/13, you wouldn't want to, in your head, sort of figure out how do I get a +3 from +2 theorem? We don't want to do that. So what I'm going to do is I'm just going to tack on in here. Okay, so I've got a +4. I'm just going to tack on a +3. Right? So I need a +3. I'm going to add in a +3. But of course I've got to balance that out, right? With a -3, right? So again, still nice and balanced, but now I know that this part is going to come with the first fraction to make my cosine, and this decision was independent of what this value was, right? So now this value will get lumped in with a -3, whatever the hell that comes out to, it comes out to, I don't care. Okay, but we'll figure that out later. So let me rewrite this again. So now I've got 1/2 times, okay, let me pull these two off into one fraction. We've got s plus 3 over s plus 3 squared plus 4. My second fraction, you know what, let me just keep the 1/2 there. My second fraction, so I've got plus 4 minus 3 gives me 1 s plus 3 squared plus 4. So right now what I see is that my cosine here, what's going to invert to my cosine term, that's fixed. That's done. I don't want to touch this anymore. I just need to fix this one because this is going to be my sine term. That's and that's not lined up right. Okay, it's supposed to be b over s minus a squared plus b squared. The bottom part is fine, but b is 2. That numerator is supposed to be a 2. Well, I can fix that, right? Okay. I can't use addition this time, but I can use some multiplication. Okay, so if I just multiply the top by 2 in my numerator, and I'll put a 1/2 in front of here. Okay, there we go. That's nice and balanced out. And what I finally get, what I can finally invert is, so I've got 1/2. I'm going to distribute this 1/2 to each of these terms to make them separate. So I've got 1/2 times s plus 3 over s plus 3 squared plus 4. 1/2 times 1/2 gives me 1/4. So plus 1/4 times 2 over s plus 3 squared plus 4. And what you'll notice is that these two fractions now identically fit those formulas we were looking for our inverse. So I can go ahead and write that down now, that the inverse Laplace transform of this function, f of s, okay, untranslating this, this gives me 1/2 e to the at, remember a was -3, cosine bt, b was 2, and this is plus 1/4 e to the at sine bt. All right, fantastic. Yeah? Okay. We love it, right? Okay. Okay, overall, again, this is not necessarily a new type of problem. This is just sort of a different skill that might come up while you're handling some of these Laplace transform problems. Obviously, there are some of these in your homework. Homework's already been posted. Make sure you guys are practicing. You're almost done. There are only 2 more lectures in this series. They both have to do with basically the same thing. In fact, actually, the next lecture doesn't really have anything to do with Laplace transforms at all. It's more sort of an algebra thing to introduce you guys to what are called Heaviside functions or unit step functions. We'll talk about those in a bit in the next section. But yeah, so again, practice. If you have questions, again, let me know. See you guys later.